If you haven't already done so, please print this handout. I want to talk about strong and weak acids and bases. So I want to contrast the ideas of strong and weak. We're talking about the strength of an acid. So if I say an acid is strong, that just means it dissociates completely in water. Whereas if an acid is weak, it dissociates only partially in water. So the strength of an acid or a base depends on how much it dissociates. So if the whole acid or base dissociates, so 100% of that acid dissociates into H plus ions and negative ions, then that's a strong acid. If it's a weak acid, then only some of the acid molecules turn into H plus ions in the water. So let's go through some examples of acids and bases. So I'm going to show you a strong acid versus a weak acid, a strong base versus a weak base. So a strong acid would be hydrochloric acid. So every single molecule of HCl ionizes into H plus and Cl minus ions. If I contrast that with acetic acid, which is vinegar, the acetic acid molecules don't all dissociate. They don't all produce H plus ions and acetate ions. Only some of them do, so hence the double arrow. That just means not all of the reactant is turning into products. So it's a partial ionization. It's the same idea when we're talking about bases. Sodium hydroxide is a strong base because every single particle of sodium hydroxide dissociates into sodium ions and hydroxide ions. There's no pieces of sodium hydroxide left over. Whereas if we look at ammonium hydroxide, only some of those particles dissociate to make the OH minus ions. So strength of an acid or a base depends on the degree to which the ionization or the dissociation happens. So let's look at some examples of strong acids and strong bases. So this is a list of common strong acids, and you are going to have to know this. So you have to know hydrochloric acid is a strong acid, hydrobromic acid is a strong acid, hydroiodic, nitric, sulfuric, and perchloric acids, those are all strong acids. So if you take any of these molecules and dissolve them in water, 100% of those molecules will form H plus ions. So the ones that I have in red, we call these hydrohalic acids. So the hydro comes from hydrogen and halic comes from halogen. So the halogens, group 17 on the periodic table. And the strong acids I have in blue, these are called oxyacids. That just means they have a high ratio of oxygen to hydrogen. So you'll notice all of these have more oxygen than hydrogen. So, strong acids, you have 3 hydrohalic acids and 3 oxyacids. If an acid is not on this list, it's a weak acid. So that's what I say here. All other acids are said to be weak. And we can say a similar thing about strong bases. Here's some examples on the right-hand side. Calcium oxide, lithium oxide, sodium hydroxide, potassium hydroxide, and calcium hydroxide. So the strong bases are the oxides and the hydroxides of group 1 and group 2 metals. So the alkali metals and the alkaline earth metals. So if a base is not on this list, we would say it's a weak base. So all other bases are considered weak. Now I want to spend some time differentiating between strength and concentration. So flip the page. A lot of people confuse the strength of an acid or a base with its concentration. These are totally different ideas, so I want to spend some time just showing you what is the difference between them. So here I have acid 1 and acid 2. Take a look at the acid ionization equation. Here we have a full arrow to the right. Here we have arrow pointing right and left. So this would indicate that every single molecule of the acid turns into H+ ions and A- ions. So this acid dissociates completely. There is no reactant left over. This acid, on the other hand, some of the molecules ionize to form H+ and A-, but remember that double arrow means there are still some reactant molecules remaining. So this is not a full ionization, or this is a weak acid. So this is a complete dissociation. This is partial. So acid 1 is my strong acid, and acid 2 is my weak acid. Now, concentration is different. I can have two separate concentrations of my strong acid. This acid is a strong acid. This acid is a strong acid. You can see there are no HA molecules in solution. It is only H+ ions and A- ions in solution. Same with over here. So both of these are my strong acid. However, this sample of my strong acid is concentrated, and this sample of my strong acid is dilute. And the same idea is over here. So both of these beakers contain acid 2, which is a weak acid. I can look and I can find HA molecules that haven't ionized. So not every single molecule has ionized. This is a weak acid, and the same thing over here. This is a weak acid because I have HA molecules unionized. However, this sample of my weak acid is concentrated, and this sample is dilute. So I just want to make that clear. You can have a strong acid that is diluted. You can have a weak acid that is concentrated. Strength and concentration do not mean the same thing. Now, if you look at the bottom of the page, this is just a way to tell whether an acid is strong or weak. So the idea is, if you test the conductivity of your acid, the stronger the acid, the more conductive it's going to be. And so if you can see that, look at the light bulb in each example. In example A, the light is brighter, and in example B, the light is dimmer. Now I want you to notice something. Sample A is a solution of 1 mole per liter hydrochloric acid. Sample B is a solution of 1 mole per liter acetic acid. So these acids have the same concentration, but we're getting different results with conductivity. So the concentration does not determine the conductivity of the acid, but its strength does. So these two solutions have the same concentration, but A is a strong acid, B is a weak acid. Strong acids are better conductors of electricity, weak acids are worse conductors of electricity.